welcome to lecture number 6, and we have been discussing two very popular method of solving a network problem. Of course, as I told you earlier that I will be considering to begin with DC sources to be present only, and only resistances are there. Of course, that I will remove soon, that restriction, just to get an idea how we apply this method to solve this network. Main thing is that in mesh analysis, identify the number of meshes. In general, number of equations to be solved is equal to the number of meshes, algebraic equation, and if you are lucky in mesh analysis, you can reduce the number of equations to be solved, provided there exists some current sources in the outer meshes. If you can identify some mesh where after this nothing is present, then that mesh current is known. That is, therefore, only for example, two meshes are there, we have to solve only one equation, this mesh current being known. Now, what happens when I consider a circuit like this? For example, you have a network like that. Suppose this current is 2 ampere and this is there, and here is another resistance, maybe another battery is present. And let us put some numbers to highlight this method, because with numbers it becomes easier, otherwise lengthy expressions. Suppose it is 4 volt, it is 6 volt, with this polarity is important, and this is 2 ampere ideal current source, and this is suppose 2 ohm, this is suppose 4 ohm, this is suppose 6 ohm, and I have to find out the currents in various branches and solve this network. Now, and I have decided I will apply mesh analysis. So, first thing I identify the meshes. Independent meshes are these two only. So, I will assign a current I 1 here and I 2 there. This is I 2, two mesh currents. Unfortunately, here I cannot say I 2 is 2 ampere, 2 ampere in this branch. But about one thing I am sure, current in this branch, because of these assumptions of this mesh current, this is true, I 2 minus I 1 is equal to 2. This is definitely true, has to be, because in this branch current is fixed, a current source is present. So, what do I do then if I want to apply mesh analysis? As I told you that suppose I attempt to write down the KVL equation in mesh 1, KVL in mesh 1. It will be, as we have learned, the sum of all the voltages in this loop has to be 0. So, coefficient of I 1 will be 6 into I 1, is not? Coefficient of I 1. Now, here comes coefficient of I 2. there is no resistance here. So, it is expected coefficient of I 2 will be 0, I mean minus 0 into I 2. Let me write that minus 0 into I 2. And on the right hand side, I will write about the sources. What are the sources? 4 volt is present. So, on the right hand side, and direction of I 1 is in consonant with this polarity of this 4 volt. So, plus 4 volt will come there. Now, there is another source which is 2 ampere current source, but as I told you, when the current source is there, it is true the current in this branch has to be 2 ampere, but voltage I do not know. Got the point? So, that becomes an additional unknown. Therefore, the rule is same, 6 I 1 minus 0 into I 2 is this, is equal to, and only 2 meshes are there, is equal to the source terms will appear. So, it is plus 4 volt, it is over. Now, here you have to then assume this thing. I do not know, this voltage is x volt, because in an ideal current source, current is fixed, but voltage is decided by what are the things connected across it. So many things are connected, some voltage will definitely appear across x. So, this can be taken into account by writing like this. But here is the important thing, this is voltage across current source, assumed voltage. I have assumed both the polarity and magnitude of the voltage x, as I have shown, assumed voltage across current source. So, this is the equation. So, what will be the thing then? 6 I 1 will be equal to 4 minus x. So, it looks like there are now 3 unknowns, 2 mesh currents and this x fellow. So, this is in mesh 1. In mesh 2, KVL. In mesh 2 will be coefficient of I 1 nothing, there is no common resistance. So, 0 into I 1, then coefficient of I 2 sum of all the resistances 6 only plus 6 into I 2, that will be there, and this should be equal to the sources. On the right hand side, sources should appear, that is the logic we developed earlier from the basics. So, this must be minus 6 volt, because direction of this I 2 and plus are opposite. So, minus 6, and then there is another source whose voltage is not known, but I have assumed it to be x here. Should I write plus x or minus x? Plus x, because this is the direction of I 2 and here is a source whose voltage is plus and minus. So, plus x volt. So, this equation was equation 1, this equation was equation 2, and this is equation 3, and nothing is to be worried about. So, 3 unknowns, 3 equations. Therefore, the point I want to stress, if a current source appears in the common branch between 2 adjacent meshes, then the number of equations are to be solved is not equal to the number of meshes, but one more, for in this problem more. 3 equations. This is 1, this is 2, this is 3, is not. But if this current source appears in the outer loop, then you really get advantage. Got the point? In any case, in normal thing, we say generally in mesh analysis, number of equations to be solved is equal to number of meshes. And in some particular cases, when the current sources are present in the outer meshes, in some outer meshes of a circuit, then you get some advantage, because those mesh currents are known. But number of variable increases when there will be current sources present in the common branch. As in this simple example, we see I 1, I 2, they are of course related by this current source, simple equation I 2 minus I 1 has to be 2, and then voltage of this current source is unknown. So, while writing down KVL equations, you follow the same rule, coefficient of I 1, sum of resistances and so on, coefficient of I 2, if there is no resistance in this branch, it is 0 into I 2, but on the right hand side this x will has to appear. Do not be under the impression this voltage is 0, you do not write anything here, it is not short circuit. Often students make mistake here, understood. Therefore, if at all you choose mesh analysis, you should be careful about these points. Try to take advantage of the fact that current sources in many of the outer loops are present. Oh, immediately go to mesh analysis, because outer loop current sources means those mesh currents are known, number of equations will be to be solved will be less than the number of meshes. If current sources appear in the common wall between the two adjacent meshes, then actually number of equations to be solved becomes more. Understood? This point must be highlighted. Once again one can apply, after you have solved, as I told you, solve it, get the values. If I 1 comes out to be negative, then it is a good practice, at least when you are beginning to learn this course, redraw the circuit, so the actual current direction. If I 1 becomes negative, put it negative, see that KCLs are really satisfied, then you can do power balance of the network as usual. Okay. So, that I am not doing. So, I am also not solving this network. So, 3 equations, 3 unknown, x appears as another unknowns. Now, I will tell you about the nodal method, that is also very interesting. And see, the point is there are several techniques. If you know those techniques, then for a given network you try to adopt a method which will reduce your labor to solve the network. That is the whole idea. Efficiently you try to solve that. So, nodal method of solving network. For solving network problem. Very good. Okay. Now, in this problem, once again let us take an example. Suppose, and first I will write down in terms of variables, I mean symbols, E 1, this is R 1, this is R 2, let there be another voltage source here, it does not matter, E 2, there is voltage here, voltage there, and there is resistance here and another resistance there. Okay. And also there is something like here. So, E1, let this be E2, let this be E3, and this is R1, R2, say this be R3, and this be R4, R5 and R6. In nodal analysis, what they say is this, that first identify how many nodes are there. As in case of mesh analysis, we identify how many meshes are there. Now, junction between two elements in general can be called a node in general. Okay. But here what I will tell is this, a node is a point where more than two elements ends are joined. For example, this I will call a node. Got the point? For example, this I am not going to call a node. Elements of R2 and this element source is ends have been joined. This I am not going to call. So, at least so nodes are these things, at least more than two elements ends have been joined, that I am going to call node. So, here you see this becomes one node, 1, 2, 3 ends of 3 elements have been joined. This I am not going to call a node, although it can be called loosely, but this is how, and this is another node and this is another nodes, and of course, this becomes another nodes. And name the nodes, for example, call it A, B, C, and let us call this to be O. The essence of the nodal method for solving electrical circuit centers around this fact. I have told you that given a network, the potential between any 2 points, what does it mean and how to calculate that, I know. For example, if you have a resistance, first let us try to understand. This is R, this is point A, suppose not in context with this, A, B in general. Then the current through this, if you say from A to B current is flowing, that is what you have assumed, then I must write I is equal to potential of A with respect to B divided by R. The same thing one can write that same R, same A B points, and if you assume the current to be in this direction, he will write x ampere, he should write V B A by x R. You must understand this point. So, depending upon the direction of the current, that is your choice, potential of A, potential difference across R is V A B. We know that. Now, if this current in the circuit, there is some other point O, and if you have calculated V A B can be written as V A O minus V B O. With respect to same point, if you know the potential of point A, with respect to the same point, if you know the potential of point B, then V A B will be nothing but the difference of these two. Why? Because you see V A O, for example, in this example V A O, I know what I mean. I have to start from O, try to reach point B. So, I start from O. Suppose I decide I will go via this path. So, potential of point A can be written as from this to this, whatever voltage will be there, that is also potential difference between these 2 points V B O. Start from O, V B O you will get, that is this drop and this drop with due regard to their plus minus sign. You calculate this, you have reached this point, is not V A O is equal to V B O. Then from this to this you have to go, and that voltage is what? V A B, whatever it will be, potential of A with respect to B, you go. Therefore, V A B is always V A 0 minus V B 0. It is an important thing, that is with respect to, but the point of reference should be same for both the ends. Okay. So, this you must understand, and then I will say that forget about this, we have understood this and this point. So, that is the thing. So, what is done in nodal method is that first you identify how many nodes are there. In this particular problem, number of nodes is equal to, which I will denote it by n, and in this case it is 4, it is that. Then what we will be doing is this, we will be, and then I say that choose a reference node. I have identified the nodes, I have chosen a reference node, and that reference node I have named it as O. At this point you must understand that any of this I could choose as reference, not necessarily this one. Got the point? I could choose C as my reference. Now, what is a reference node? With respect to this node, I will calculate the potential of other nodes. That is, I am going to find out VAO, VBO and VCO. Got the point? If you have had chosen C as your reference, then you will say I will calculate all the potentials of the circuit with respect to this point, VAC, VOC, VBC. So, in this case I have just arbitrarily chosen O as a reference node. Generally, one observation is this, people choose that point as a reference node where many ends of have been joined, more than 3, 4, 5 ends are joined, that point. We will come to this. So, I have chosen O as a reference node. Then I know what is the meaning of VAO. VAO means potential of A with respect to O, potential of B with respect to O, potential of C with respect to O. So, this is E1, E2, E3 and E4. Now, I make one statement that in a network my final thing I have to calculate what will be the currents in various branches. For example, in this branch, what will be the currents. Now, as I told you, current in an resistance, if you have x and y as its two terminals, and if you want to find out current in this direction I, then you must write I as potential of x with respect to y by r. This is crucial. There you do not fumble, this is the thing. Now, I am saying that if by some means, by hook or by crook, if you can somehow know these voltages, these 3 voltages, somehow you have been able to calculate, doing what that we will discuss. But if I say that in this network node that VAO is known, VBO is known, say it is 10 volt, VBO is 5 volt, VCO is 12 volt, suppose I say that, then I will say the calculation of branch currents will be just very simple now. Why? Suppose these are known, then I am saying that all the branch currents can be calculated using those 3 information alone. How? Let us see. For example, to calculate the current in this branch, say I want to calculate this current in this branch. Although this is not named, let me give a name x, this point let me call it x. Then what is this current? I2 say this branch current I2 will be Vx potential of A with respect to x divided by R2. Grab the resistance in that branch, find out voltage across that resistance divided by R2, and no one can contest me, this is absolutely correct. Now, this Vax, this is the crucial step. I will write it as Va0 minus Vx0 divided by R2. This will be this current I2. Now, then I will say that okay, look here, Vx0, now this point is crucial, Vx0 potential of x with respect to O, because these are the things I know, Va0, Vb0, Vc0, somehow I know. So, Vx0 will be how much? Okay, you know Vb0, that means you have already reached point B, then point B you try to go to x. So, what it will be? It will be Vb0, then plus to minus, so minus E2, that will be the thing Vx0. Therefore, you see I2 then becomes I2 then become Va0, then minus Vx0 is nothing but this quantity minus Vb0 minus E2, is not, and that divided by R2. It will be equal to Va0 minus Vb0 minus plus E2 divided by R2, this will be the current. So, can I not calculate I2, because I have told you that Va0, Vb0, Vc0 I am supplying you the values. Okay, I2 can be expressed in terms of that, E2 is after all a constant EMF value. So, these things are known, I2 can be calculated. Take this current, these branch currents, say this current is I 4, grab the resistance R 4. So, I 4 will be equal to, and this point no name is given, let us call it y. So, to be consistent with this expression here, I can write I 4 will be nothing but V B y, potential of B with respect to y, divided by R 4. This will be the current. Then what do I do? V B y can be written as V B 0 minus V y 0 with respect to same point, divided by R 4. This will be the current. Now, the big question is, what is V y 0? From 0 you try to go to y, it is plus E 2, nothing else. So, this is equal to V B 0 minus E 2 divided by R 4. Oh, I 4 can be calculated, because V A 0, V B 0, V C 0 are known, very simple. Similarly, I 6 can be calculated, one can go on adding, and I am now telling it will be simply, you try on your own, it will be V C 0, and from this to this minus potential of this point, if you call it Z, B Z 0 is minus E 3, plus to minus. So, minus E 3 divided by R 6 and so on. Similarly, this branch current I am very quickly writing, it will be this branch current, say I 3, if I say I 3, it will be equal to V A 0 will be there, minus potential of this point with respect to this, and that can be translated into V C 0 minus E 4. And divided by R 3, is not. So, in fact, for any branch you can do it. Therefore, first the point to be noted is this: identify the number of nodes, and I just told you today that if these node voltages are known with respect to a reference node voltages, say here n equal to 4. So, 3 node voltages, one of them you will choose as reference, and there is no condition that O is to be chosen as a reference, any one of them can be chosen as a reference, I have chosen O. So, the other 3 node voltages with respect to that reference node, if these potentials are known, I am telling you, you have almost solved the circuit, because the branch currents, any branch current in this type of network can be expressed in terms of those node voltages, as example I 4 is V B 0, and so on. I 2 is this one, V A 0, V B 0 plus E 2 by R 2. Therefore, calculations, what is the essence of the thing? In any branch, grab the resistance whatever is present and apply this rule. This is the fundamental Ohm's law. Voltage across this resistance is the current. V A x by R 2 is current from left to right, and V A x can be written as V A 0 minus V x 0. So, from O try to reach x, and you will find that can be expressed in terms of other node voltages and some sources present. Anyway, we will continue with this in the next class. Thank you.